Hi everybody, welcome to Capgemini's World Energy Markets Observatory. This is the 26th edition. My name is James Forrest. I'm the Global Industry Leader for Energy Transition and Utilities. I'm delighted to be joined today by Colette Lewiner, Florent Andrion and Peter King. As you can see, we've done things a bit differently this year. We've got 4 distinct chapters that you can dive into independently. We hope you enjoyed the first chapter on the geopolitical situation. This is the second chapter on the progress on low-carbon technologies.
So on low-carbon technologies, we have spotted a few technologies: solar and wind, which are renewables, intermittent renewables; nuclear energy, which is low carbon; stationary batteries, because intermittent renewables need storage; hydrogen, we have looked carefully at the situation to come to interesting conclusions. Grids are very much impacted by intermittency of solar and wind and need more flexibility. This year we have covered 2 subjects which we didn't do the last years, which is geothermal and bioenergy, because stability of grids will be a problem in the future, and these are producing green heat that goes directly from heat to heat usages. And then CCUS that needs to develop.
When we look at solar and wind in 22 and 23, the increased production from solar and wind experienced notable growth and has beaten all the forecasts, and that probably will be the case as well in 2024. And that's driven notably by favorable policies and increased investment. This growth is largely driven by China, which accounts for 63% of the newly added capacity. In 23, solar energy saw a remarkable growth of 73%, while wind energy, although expanded, experienced a slightly more moderate development. Thanks to this acceleration, global renewable energy capacity reached a record high of 462 gigawatts added this year, compared to 340 gigawatts in 2022. And for the first time in 2023, renewables surpassed 30% of the global energy production, mainly due to increased solar and wind capacity. Since 2000, the share of renewable has risen from 90% to 30%, with wind and solar accounting for a bit less than 50% in 2023. This momentum is critical for supporting the global energy transition and reducing dependency on fossil fuel. However, continued investment in this technology is still needed to accelerate and continue the rollout of this technology. Now, when we look at investment, 2030 has been also a record year for renewable investment and reached unprecedented levels at nearly $400 billion, which is a 15% increase compared to 2022. A significant percent of this investment, more than half, has been directed directly towards solar, with $222 billion invested, an amount that exceeds the approval from 2020, which were 2.5 times less. Wind energy saw a slight recovery in 2023. The number of new onshore wind projects fell short of expectation. It is essential for government to continue support investment in these technologies to ensure sustainable and resilient energy future. Now, while we witness dramatic growth in renewable capacity, there is also a challenge in terms of profitability when we compare renewable assets to fossil fuel-based assets. And that's notably the case because there is now an increased competition in the renewable industry. The land are getting more harder to find, but there's also much more players in that industry. And as well as in many regions, we also see the end or reduced support tariffs because now renewables are competitive. So that means that renewable power producer needs to compete on a non-merchant world, which is putting an increased pressure on profitability. So we are now witnessing an increased interest of renewable players to reduce their operational expenditure and capital expenditure throughout all the life cycle of renewable assets. And it's, I would say, the end of the invest and forget era that we have known for years. So they are now looking at cost reduction measures across all the different levels, from engineering to massification of procurement for the different components, but also implementing operational excellence program across the different assets during their operation and maintenance, plus I would say innovative and better financing as a lever to increase profitability. A few other levers to mention is innovation and digitalization. Digital solution can help to reduce the cost of maintenance, but also increase the efficiency during the engineering to optimize the production load factor. Last topic, it's the diversification, and we see, for instance, an uptake in the battery storage. First, to counter, I'd say, the negative power price, and we'll mention it a bit later, but also to find other areas to get revenues, for instance, in coupling renewable to EV storage or to renewable hydrogen. And as you can see on the graph, on the chart, it's also a way to reduce the gap between the profitability of oil and gas assets with renewable assets.
So in 2023, we reached peak emissions from electricity generation. As you can see on the right-hand side there, fossil fuels will now represent 40% of overall electricity generation. However, fossil fuels still dominate the overall energy supply. On the left-hand side, you can see that oil, gas, and coal account for 75% of our primary energy consumption. But is primary energy consumption the right concept, the right way of measuring it? We contend it's an outdated concept. We think it ignores a few things. Firstly, new energy services are much more efficient. Secondly, a lot of effort, a lot of energy is expended in generating electricity from fossil fuels. And thirdly, a huge amount of energy is used in finding and distributing fossil fuels. So the world would need a lot less clean electricity if you replaced all of the energy services today with clean electricity. We estimated if you did that replacement, so if you took all the energy today and you replaced it with clean energy, you would only need 40 to 50% of that primary energy consumption. So we think it's best to measure final energy demand in terawatt hours, not primary energy consumption.
Okay, so let's go to another low carbon technology, which is nuclear. Nuclear was recognized worldwide as, and it is, a low carbon technology, but Europe took a lot of time, and it was only last year that it was recognized as a low carbon technology. It's only for political reasons. Existing reactors, the good news is in 2023, there was safe operations everywhere. And just as a figure, the 140 nuclear reactors have provided 9% of the world electricity. You have construction of large new reactors, which are third generation reactors. In 2023, there were 6 reactors connected to the grid, and more particularly in Europe, Olkiluoto in Finland was connected. In 2024, Flamanville in France was connected. And good news also is that 2 Japanese reactors have started again, and they have the Japanese government has a plan to have more reactors restart after the Fukushima accident. Developing our small modular reactors, these are reactors that are on the same technologies as the large ones, meaning using water as a way to limit the nuclear reaction. And we're going to talk afterwards on AMR, which are advanced modular reactors, which are using other processes than light water or boiling water reactors. There are many concepts. Each country, or more than each country, has a SMR concept. There are only 2 in operations, 1 in China, 1 in Russia, and 4 under construction. The plus and minuses compared to large reactors is probably they are smaller, so more easy to construct, more easy to finance, easier to connect to grids because they don't put too much electricity on the grid, which can have a problem on balancing of the grid. The problem they can have is cost. We saw it with NuScale. NuScale had to stop a project in the US because cost went up nearly twice times. So it means that you need to amortize the studies you're going to do, notably the safety studies on a large number of reactors, meaning that those reactors should be able to be built in different countries if the safety authority agree on the same safety norms for the different reactors. I think personally there will be both big reactors and SMRs. Now, the question here is will nuclear help to reach the climate objectives? You can see this chart quite interesting. In a nutshell, if we do nothing, then the present reactors will end their lifetime. We'll construct some new ones, some SMRs, but it will not be enough. So to make it happen, you need a few things. First, you need to extend the lifetime of existing reactors. The US has extended some existing reactors to 80 years, thinking of 100 years. In France, for example, we're only at 50 years. Of course, it can only be done if it is safe. Then boost the construction of new large reactors. Here you have a real problem on financing it. In the Western countries, it is an issue, has to be solved, and also develop, of course, SMRs. For that, you need a reliable supply chain and good cooperation between the utilities or the constructors of nuclear plants and the supply chain. And also you need to prepare and get the right skills, both blue and white collar skills. As a small example, in Europe we don't have enough welders, and we need to find how to increase the number of available welders by training, by taking welders in other countries, etc. Now, a question that many people are asking, will we have enough uranium, because we are seeing a big expansion on nuclear power? First of all, uranium is a very well spread mineral in the world. It's not at all like oil, which is concentrated in a few regions. Here you see on the chart where today the uranium is coming from, and what's interesting is to see the black part, which is Kazakhstan. Kazakhstan has become a big uranium supplier over time. Prices have gone up, but not at record levels because of this possible tension. Personally, I believe that we have enough resources. First of all, utilities have a lot of stockpile, a few years of uranium stockpile. Then new technologies like breeders can enhance the use of uranium by a factor of 200%. China and India have projects of reactors using thorium. Thorium is well spread in the world. And finally, uranium is a very small, a few percentage of the end cost of the nuclear kilowatt hour. So perhaps in the short term we will have tensions. Now in the long term, I think there will be enough uranium in the world.
So let's look at batteries, in particular stationary batteries. So stationary batteries are those that are connected to the grid or people have at their homes. And this demand and this supply is growing very rapidly, but it's still not enough to meet the needs of renewable installations. Again, and a recurring theme throughout this report, China is dominating. A key point here, though, is the business case for batteries remains fragile. It relies very heavily on local market regulation fitting the needs of batteries. And isn't it crazy that the business case for batteries relies on price instability? So in places like Texas, California, Germany, it's price instability which is driving the profitability of batteries. Technology is advancing rapidly and it's very promising. But we think the reality is that the EV use of batteries and the EV development will really lead here, and that the utilities and the stationary batteries will follow the development in the EV technology.
If we now look at clean hydrogen, which has been overly overlooked and benefited from an excessive hype, it's now being going through a strategic reassessment of the volumes. If you take the International Energy Agency, now forecasts that the global hydrogen market will reach 150 million tons by 2040. 2030, with approximately 70 million tons of low carbon hydrogen. And that's a revision compared to the previous forecast of 212 million tons, so significant. It still represents a 50% increase compared to the current demand of 95 million tons. This revision is accompanied by refocusing on industrial use, where we have less alternative for decarbonization, and you can see on the graph in the carbon-intensive hydrogen will be replaced by low-carbon hydrogen, such as, for instance, in the steel manufacturing or in the chemical industry, as well as to produce the first electric fuels, such as e-kerosene for the aviation industry and e-methanol for maritime or long transportation. This massive need of hydrogen for those hard-to-abate industry is evidenced by a quadrupling of the number of clean hydrogen projects reaching their final investment decision, from 102 projects in 2020 to 434 projects in 2024. When we speak about hydrogen, we must also compare not peers with Apple and being able to also understand that hydrogen will be used differently depending on its usage. For instance, if you want to use hydrogen for road mobility, there will be different steps before it can be used for mobility application. Likewise, if you look at it for industry, or for e-methanol, the step may be different, and that will impact, obviously, the cost of production of these hydrogen-based derivative products. And that means that those products will need to be compared with the alternative fossil fuels. So, for instance, if you look at clean hydrogen for steel, there's also a mechanism to consider when you compare the price, such as a carbon tax, for instance, which can make this low carbon hydrogen competitive in some application, while others will benefit, for instance, in Europe, of regulation that will support the incorporation of low carbon hydrogen, for instance, in the aviation industry, to support the production of e-fuels.
Okay, now we're going to talk of the grid. The renewables that are intermittent are impacting strongly the grid, because the grid needs to balance at each moment the generation with the demand. We can see as an example here the number of negative hours in Europe, and you see it has, in 2023, it was more than 6,000 hours compared to around 600 hours in 2022, 10 times more. Negative hours meaning that you have too much electricity on the grid, and then the grid operator needs to take measures. And measures that are taking is curtailment. They oblige the renewable generation to stop. And just as an example, those curtailment figures are quite high. In Germany, it was 8%, US around 5%, China probably around 5% as well. This has a very negative impact on the profitability of both renewables and nuclear, because sometimes nuclear is also curtailed. It has a negative impact on all generation that has a high capex, because then you cannot amortize your capex on enough hours. It also translates in the real cost of renewables, of intermittent renewables, and this is our chart showing what is the real cost. You need to add to the LCOE, the levelized cost of electricity, what is called the firming cost. How much dispatchable generation you need to have to balance your grid with those renewables. And you can see here quite clearly the LCOEs for solar and wind. This is in different states in the US. You can see in the dark blue or light blue, and then you see the firm electricity cost in yellow, and you see it can sometimes more than double the real cost of renewables. So it is something needed to take into account. It's another translation of the fact that you cannot manage a grid with only intermittent renewables. You need dispatchable electricity. In Europe, we have nuclear, which is a low-carbon dispatchable. In other places, you need more batteries probably, and perhaps to keep some CCGTs, gas-powered plants. Now, let's look at another point on the grids. It's investment. You see investments are picking up, perhaps not quick enough, by the way. And you can see investments are picking up slowly in the US, that has very old grids and needs more investment, certainly. China has problems with the grid. It has a very high voltage grid, which is very high voltage from one region to the other, but the local grids are weak sometimes, which explain the big percentage of curtailment. Then Europe is also increasing. For that, you need the right regulations, and if regulations are too tight and doesn't allow the operator to invest, doesn't happen. So it has also to happen to be able to use as much renewables as possible. Another way of balancing things is not to go through electricity for heat, and to use sustained heat for heat needs. And heat and cooling are 50% of the global final energy consumption and 40% of the global emissions. And today, heat generation is 75% fossils. We probably need to develop more those sustained heat sources. We quoted here geothermal. Geothermal has a potential, and many countries want to develop it. In France, we had a plan to develop geothermal. You have different types of geothermal because when you dig very deep in the ground, of course, you have heater source of energy. You produce vapor. If not, you produce hot water at medium or deep depth. And what's interesting is in very high depth installations, sometimes you find lithium in the brimes. And it is the case for east of France, for example. And what's also interesting for the medium and near surface depths, you have to associate this geothermal heat with heat pumps. And you're going to improve quite a lot the heat pumps yield by doing that. Another green heat source is bioenergy. And modern bioenergy is the largest renewable energy sources. Of course, in the world, biomass is the largest energy use, but often biomass is in developed countries and in poor conditions. You can see here that biomass and biofuel could be more developed. And to reach the climate objective, you would need 8% growth. You can see the different countries in the world, the developed and developing country. And for example, for ethanol use, you find Brazil that for years and years has already cars that able to use ethanol. So here also you have a green source of heat that could be more developed. Finally, another technology, carbon capture, usage and storage. It's important. If you think that countries that have coal and using coal today are often countries where coal is a domestic resource. In Europe, you have Poland, for example, you have China, of course. And so you need to develop this technology. It's going very slowly. Why? Because installations are quite big, so need to finance them. And there is not a bankable model in the absence of enough carbon prices or carbon taxes. And we don't have enough around the world. Carbon markets are covering a few percentage of the total carbon CO2 emissions. So you need to find bankable models. Recently, UK put for the CCUS CFD model, and in the US, ERA is providing subsidies for CCUS. Also, China is developing more CCUS, which they really need. So technology to accelerate, but it is certainly needed.
Let's have a look at demand-side flexibility now. So that's the ability of users to shift when they use their electricity or their energy. And it's essential to renewables and clean energy that we have this. So let's look at some of the technologies. So heat pumps have definitely accelerated, but in the last 2 years, the rate has stalled as subsidies have been withdrawn. Domestic batteries, again, have accelerated really well, but again, the scale on the left-hand side of this graph is really important, and it's not nearly where we need it to be in order to make a real step change in domestic use. And then on the right-hand side, we've got two really interesting technologies which can both help and hinder. So air conditioning, as peak temperatures around the world increase, the demand could increase, so that could put greater strain on grids. But equally, air conditioning could be used as a way of balancing supply or balancing demand as when needed. And similar for data centers. So data centers, IT's use of data of energy could double. But again, we could shift compute power around the world to help balance. One of the things we really need to focus on is the acceleration of the circular economy. So today, only 7% of materials are recycled. There are initiatives underway, and the chart shows some of those. So a battery passport scheme to assure origin of the batteries, reuse obligations, lithium recycling. Colette has mentioned lithium many times as a key resource. Solar recycling, wind recycling, and then again mentioned earlier by Colette, but essential to this is the extension of the life of nuclear power stations, and that could really be a lifeline for us.
Our overall conclusion of this second chapter is while progress on technologies has generally been good, we really need new market mechanisms to accelerate these technologies. We need to replace the current subsidies with new market mechanisms. We need mechanisms for business development models for energy storage, electricity storage. We need mechanisms to maintain intermittent renewables profitability. Colette talked about the contracts for difference that have been successful there. We need mechanisms to finance new nuclear. We need mechanisms to keep gas-fired power stations ready for grid balancing. And also we discussed we need a new mechanism for a bankable business model for carbon capture and storage. We also need to increase the grid flexibility, increase the storage, and make better use of data. Thank you, Colette, Florent, and Pete. Please do look at the next chapter on our recommendations on how to get to net zero.